Welcome back to the lead channel. This should be the last video that sums up the IB portion of kinematics, or 2D projectile motion. Before we start looking at the quantitative side and the calculations for 2D projectile motion, let's go ahead and try to look at some of the qualitative aspects of 2D projectile motion and how they will influence our calculations or things we need to watch out for when we are doing calculations. Coming back to some of the key points with 2D projectile motion, number one, we know there is acceleration due to gravity in the vertical direction. However, when I see a lot of students work, oftentimes I see students use gravity in the horizontal direction. Well, first of all, we assume there's no air resistance, okay? If there was gravity acting in the horizontal direction, if you were sitting in your desk right now, and if there is horizontal acceleration, you'd be thrown against the wall immediately and stuck there without being able to move so much. There can never be horizontal acceleration, especially not gravity. Gravity doesn't act on us horizontally. With no other forces acting on this object, we deal with no acceleration in the horizontal direction. Now, before we start calculations, I just want to show us visually how 2D projectile motion really looks like two individual one-dimensional motion put together on a piece of paper. When we dealt with one-dimensional motion, we've thrown something upwards. In the beginning, you start off with an initial velocity and something gets thrown upwards, which means over time, gravity is going to decelerate it as it reaches the top. At the very top, it stops momentarily at its maximum height, and then it begins to fall back down again. And in a one-dimensional projectile motion, you can see how everything is symmetric, including the time it takes the object to go up and the time it takes the object to come down. Also, the initial velocity, the initial speed from when it was thrown, all the way to when the object comes back down, these magnitudes are the same as well. Okay, equal and opposite. So this is vertical projectile motion, and I staggered the drawing a little bit because I wanted us to see how the dots look like. Otherwise it'd be smeared in the same place. Okay, so that's what it looks like for vertical projectile motion. If you throw something on an angle, you're going to see this object exhibiting 2D projectile motion, and the motion is kind of gonna look like this. There's my terrible drawing of it. And if you took a timer and then you measured the time at the same intervals as you see in just the vertical motion, you probably find something that looks like this. That's the initial. You get this one here, this one there, etc. and whatnot. Okay, so then this is where you would see the ball or the object at these points in time. Now, this is something that I want you to notice that's very interesting. Take a look at the horizontal spacing of each of these dots. And of course, they're not going to be exactly perfect because my drawing is very bad, but roughly you can see the idea. So if I go here, this point is over here, and over here, this guy's over here, and etc. And you can definitely see how my drawing is really bad. I can't draw parabolas very well. Oh, especially the end. The end is terrible. So notice one thing that's interesting about these particular points in the parabola. Notice that they are pretty much equal distance to each other. So we have something that was thrown initially with a certain initial velocity, and then if you take a look at the spacing of these dots, so notice in contrast to the vertical motion, just the vertical aspect of 2D projectiles, the spacing is much varied compared to the horizontal one. So that really speaks to the fact that in the horizontal direction, the velocity is constant. So I'm going to write Vx for horizontal component of the velocity. This is constant, doesn't change. However, if you take a look at the vertical components, the vertical velocity does change. And that's from breaking your initial velocity into x and y components. Because we are dealing with 2D motion, all your vectors can be broken down into x and y components. So that means whatever horizontal component or horizontal velocity the object started off with in this motion, that's what it stays that way for the entire trip. So in fact, this initial x velocity is the same throughout the entire trip. It's constant. So the point of this drawing is to show you how 2D projectile motion is essentially a combination of 1D vertical projectile motion plus horizontal constant velocity motion. So this is what I want you to see when you see a 2D projectile motion. It is essentially two individual 1D problems. The key point from this is also how the x and the y components, vertical and horizontal components, are independent of each other. Because notice that whatever happens vertically doesn't influence what happens horizontally. So that means when we're doing our calculations, we are also assuming that the x and y components are independent of each other as well. But one thing you notice that's interesting is whenever you try to find the time or you're trying to find something at a certain point. So let's say you want to find the maximum height, okay, and you know that the maximum, and you want to find how far horizontally this object's traveled. If you know the time it takes the object to reach the top, the maximum height, notice that if I want to calculate the horizontal displacement, all I need to do is I need to go down to my horizontal piece and then look at how much time has elapsed to get me to there, which means the time aspect is the common factor. Meaning if I know the time that it took the object to go horizontally, I can find the same time that the object took to go up vertically. And that is where my object will be in its 2D parabola. So if I look at the time, let's say I find the time here, I can see how far it's traveled horizontally, and I can look at how high it is up vertically as well. Same thing with this point. If I want to see how far it's traveled horizontally, I look at the horizontal piece. If I want to see it vertically, I look at the vertical piece. So I can map out my 2D projectile that way. And we'll see how we do this from a calculator perspective. So let's summarize this with a little bit of drawings here. If I took all of these points and I broke them up into certain pieces, and let's say I wanted to draw the velocity components, the x and the y components, at every point on this projectile, we've just seen how the horizontal component doesn't change. And then the vertical velocity changes due to gravity. So notice that on our little drawing, our dots progressively became smaller apart or wider apart depending on the velocity. So in the beginning, it has some very large vertical component, and then that's going to decrease over time, becoming a momentarily zero at the peak of the parabola. When it comes back down again, it's going to get increasingly larger, very similar to that on the left-hand side, but in the opposite direction. So that's for the vertical velocities. And now for the acceleration, we know that horizontal acceleration should be 0, but for the vertical acceleration, this is always 9.81 meters per second squared in the downwards direction, okay? So here's a little summary of 2D projectile motion with all the vectors. And here I wrote it again, how all of your horizontal and vertical components work independently of each other, okay? They work independently of each other. Great, so now let's do a problem together. Let's read the problem together. I'm going to show the work on the right side, just like how you would do it, okay? Or how you would write it on your sheet as well. We have a cannon fired my spoon at 125 meters per second at 55 degrees above the horizontal. So if I had to draw this, it would probably look like this. And now for A, we want to find the horizontal and vertical components of the spoon's initial velocity. And here we're going to assume for this problem that the air resistance is negligible, or that there is. So we draw this over here where I'm going to show the work. And then the first thing ever when you're doing a 2D projectile motion is if you don't know what to do, break down the vectors into their components first. That shouldn't take any thought in terms of solving the problem. Just do that first. Do the step first. So I'm going to draw it here. Initial velocity is 125 meters per second with an angle of 25 degrees. We're going to find the horizontal component as well as the vertical component. All right, so now we do both of these steps. Now I'm actually going to start skipping a few steps in terms of the trigonometry because hopefully at this point you have done a lot of those problems already. You should be able to see these connections as quick as we're doing right now. So for the for the vertical piece, we take a look at our Pythagoras, we have the hypotenuse and we're trying to find the opposite. So in this case, we're looking at sine theta. And we're going to look at the sine theta of u times sine of 25. And how I got here, like I said, I did skip a step in between because I want us to be able to see the trig ratios and being able to write this right away. So do a few more practice if this is not apparent. And we have ux, I have u, and this is the adjacent side, so I'm going to look at cosine of 25. And again, if you have no idea what I did here, write down your trig ratios and then solve for uy. Okay, so these are what we start off with. We put in the values, which is 100, I'll do it here, 125 times the sine and cosine, and you put in your calculator, and you should get the following. So y you should get around 102, I believe. But rounding it to two significant figures, we have, oh, I realize it's my bad, the angle is not 25, it is 55. Let's change that to 55, change that to 55, and then change the rest to 55, and not 25. Putting this back in, 102.394. Or this is 1.0 times 10 to the power of 2 meters per second to round that off. On the horizontal side, we have this one equal to 71697, which gives us 72 meters per second. So those are our horizontal vertical components. B, we are going to find how long it takes a spoon to reach its maximum height. To do this one, for the rest of these problems, what we're going to be doing is we're going to be splitting off all of our vectors, values, into their x and y components. And doing that, we're going to have to draw a table. The idea comes from this fact that in a 2D projectile motion, you can analyze this as two individual 1D projectile. So I can just, if I just want to find a time it takes to go up to the maximum height, all I need to do is look at my vertical motion only. But first, let's draw this table. So I'm going to draw for x components, I'm going to write on this side. For y components, I'm going to write on this side of the table. I know that in the horizontal direction, I know that Vx, which is equal to my initial velocity in the x direction, as shown in the diagram above, this is equal to 71.697 meters per second. Notice I'm keeping all the significant digits. And my vertical component is 102.394. And hopefully you are able to save this into your calculator. If not, this is what we have. We also know that in the vertical direction, we have acceleration due to gravity, which is negative 9.81 meters per second squared. We also know that whatever time that we use is interchangeable between the two tables, between the two sides, because t is the common factor, as what we wrote up there. T is a common factor that we can use to track the motion horizontally and vertically by going through to the the middle to the 2D projectile. So we have t going to be the same as the t here. So specific to this question, we want to find the time it takes a spoon to reach maximum height. For this specific question, I will choose my final velocity to be at the very top of my projectile. So I'm going to choose my maximum height, my time to be up here. My velocity up here in the vertical direction is 0, similar to in 1D projectile motion, the velocity up there is 0. So I'm going to write this down here. I'm writing it in blue ink because this is specific to my question, or specific to question B. So given all these values, I think we can go ahead and find the time. When we are doing the calculation step uses the kinematics equations like always. But when you're writing a kinematics equation, it has to be relative or using only components in either the horizontal or either the vertical. You can never interchange values in the same kinematics equation. So in this problem, I am mainly going to be dealing with this side of the table. So as I'm writing out my kinematics equation, I look at my table, I look at, the one that uses all 4 of these values is this one. And I'm gonna solve for time to get my time. And this is 0, of course, so I can just move this to the other side, which then gives me negative u equals at, then divide both sides by the a. I get t is equal to negative u over a. Then I can put in my values. And notice when I look at UAT, this is in the vertical direction only. So that means my U is my vertical one, and acceleration is my vertical acceleration, which is gravity. So this is, I believe, is 102.394, and it's negative, divided by gravity, which is negative 9.81 meters per second squared. After I solve this, I should get t is equals to roughly 10 seconds. That's pretty much what I'll do for this first part of this video. My second part of this video is going to look at the further calculations. So keep this on the side, and a recap would be looking at how 2D projectile motion is essentially 2 individual 1D motion problems. Otherwise, stay tuned for the next part of 2D projectile motion. Signing off.